department or physical location, reduce overhead caused to each host. Like I said earlier, the more broadcasts they listen to, the more CPU time they need. Reduce load on spanning tree protocol. Spanning tree protocol is really another session, but by combining VLANs and spanning tree protocol, you can divide up traffic so different VLANs go across different trunks back to your central location. So it gives you some more flexibility there. Streamline your network traffic. You're cutting down so only these systems are talking to each other. It's much more efficient that way. What's more efficient, if you're trying to talk to a single individual or if you're trying to talk with a group of people? You're going to get more communication done with that one person than you are with a group of people trying to fight for everybody else to hear them. Enforce better security, and again, separate out traffic. Now, networks without VLANs. They look kind of like this. You have a switch, all computers are on it talking to each other. That's default network 101. You go and get a switch and put it in your house. This is what you're going to get. This really isn't what you want in an enterprise situation. You want something more like this, where you can divide up, like an accounting department, public relations. You can segregate it by group. So these guys can talk to each other easily on broadcasts. These guys can talk to each other on broadcasts. Say you want these guys to be able to get to them, but you don't want them to get back to the accounting department. You can do all of that with VLANs. Very flexible, gives you so much more control over your network and who's talking to who. Segregation by location. If you have multiple buildings and you have a trunk line or an uplink between them, most likely you're going to have something like 100 megabit or a gigabit going off of a switch. It's going to be very fast communications like that. Whereas, if you have different locations where you have a WAN link, you can rent these. They're much more expensive than just running the cable on your own, or you have actually wire that you run between your building and the building next door. This link is going to get saturated. If all you have is one network, you're going to get the broadcast from all of these bleeding across that link over to here. Wouldn't it be much better if only the traffic from these guys that need to talk to these or these need to talk to these, if that was the only traffic going across this link? That's going to be much more efficient. You're going to use your bandwidth in a much better way, and you're not going to, and if you just have it all there, people are going to be complaining, oh, it's horribly slow for these guys to talk to these guys. That's because it's all being eaten up by broadcast traffic. You eliminate that broadcast traffic, and bam, this link is going to be much more efficient, and people are going to go, wow, you're a genius. Trunking protocols. In order for traffic to go across an uplink like that, you have to be able to tag that traffic. So as it goes across from one switch to another, that switch has to go, okay, I'm getting it, now what VLAN do I have to put it back out on? And you do that through VLAN tagging. And the two standards for that are ISL and 802.1q. Okay, let's give you an example here. We have this network divided up into, what is it? 2 VLANs with a trunk interface between 2 switches. Now, if communication is just happening within a VLAN, it's just going to get an Ethernet frame. So, your typical Ethernet frame. Now, once it gets to the switch and the switch goes, hey, I need to send this over to, another port or another VLAN, it has to be able to add the VLAN ID onto that Ethernet frame, so that when another switch receives it, that other switch goes, oh, this is from VLAN 2, goes to the switch tags on, hey, this is VLAN 2 traffic. The frame gets over to the other switch, the switch looks at it and goes, oh, this traffic is meant for VLAN 2. It rips off the VLAN ID and sends it out the appropriate port on VLAN 2. It goes, oh, hey, there's the MAC address of the guy this is going to. I rip off the VLAN ID and hand it to him. Or if it's a broadcast, it rips it off the VLAN ID and sends it out every port on VLAN 2. Now, the older of the two protocols, or standards, is inter-switch linking. It was created by Cisco years before IEEE created 802.1q. It is Cisco proprietary, and it's really being phased out. Some of the newer switches don't even support ISL anymore because everybody is using 802.1q, the open standard, which it does some things that are better than the ISL standard. IEEE took the ISL standard, kind of looked at it, got other input, etc., and built a better protocol. ISL fully encapsulates the original Ethernet frame in an ISL header and trailer. So you have the original Ethernet frame down there. It tacks on a beginning, a header of 26 bytes, and a CRC of 4 bytes at the end. The header includes several fields, including the important ones, the VLAN field and the MAC addresses of the sending and receiving switches. That's something very different from 802.1q. 802.1q is the more popular standard. It's what everybody uses nowadays. Uses original source and destination MAC addresses, where, as before, if it went from switch to switch, the switch would put its MAC address and the destination MAC address of the switch. With 802.1q, it keeps the MAC addresses of the originating and end receiver of the frame. It also inserts an extra 4-byte VLAN header into the original Ethernet header, and what that does is it forces a recalculation of the original frame check sequence, or FCS. So as you see down here, there would be an original Ethernet frame, and then down here you can see where you have the original frame, and after the source address, it inserts this information in here: type, priority, flag, and VLAN ID. VLAN ID probably being the most important piece, and priority is in there, and it helps with your QoS. Now, ISO and 802.1q compared. ISL is defined by Cisco. 802.1q is defined by IEEE. Which one inserts a 4-byte header? That would be 802.1q. Supports normal range, which is VLAN 1 through 1005, and extended range 1006 through 4094 VLANs. Both of them do that. Allows multiple spanning trees. ISL does, and 802.1q now does. Older versions didn't necessarily do that. And uses a native VLAN. That would be 802.1q. ISL did not do that. IP subnets and VLANs. They kind of go, they are separate, but they go hand in hand. Devices in a VLAN need to be on the same subnet. If they're in the same VLAN, you want them to have the same IP address range and have the same gateway out so they can all talk to each other. If they aren't in the same subnet, they're on the same VLAN, they still can't talk to each other because they don't realize that computer's address is just on their same VLAN. Devices in different VLANs need to be on different subnets. You want to be able to send from one VLAN to the other. They can't be in the same network range. VLANs are layer 2. Subnets are layer 3. This is why they're really different things, but they still go hand in hand. One relies on the other. Routing is needed to facilitate inter-VLAN communications. So if you want to have one VLAN talking to another, you have to have a router here and there, somewhere. This gives an example of, we have VLAN 1 with 10.101.0, VLAN 4, 10.104.0, 3, 3.0, 2, 2.0, and they can all talk to each other. But that's all they can do without this router. If you don't have a router, all they can do is talk to each other. You have to have a router to route traffic between different subnets. Now, this is showing a router on a stick configuration, which is really all you need to know about in a CCENT level. But really, in a real enterprise environment, you're not going to have a router up here and a switch. You're going to have somewhere in your network a layer 3 switch, which combines a router and a switch both. So it's a switch that can do routing. Routers are layer 3 devices, switches are layer 2. This guy operates on both layers.